Hi friends, welcome to our YouTube channel Raj Academy. The meaning of this lecture is to discuss about the analog communications or the communication systems of the IES Prelims questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes on mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 81st question. So is a question here. A super heterodyne receiver is to operate in the frequency range 550 kHz to 1650 kHz with the intermediate frequency of 450 kHz. Then R is equal to C max by C minimum denote the required capacitance ratio of the local oscillator, and I denote the image frequency in kilohertz of the incoming signal. If the receiver is tuned to 700 kHz, then so we need to find what is the value of the R and also the image frequency we need to figure out. So therefore, out of the four options, option A is the correct solution of this question. So let's solve this numerical. So for this super heterodyne, the incoming signal frequency has to lie in this range. In the question they have given the range is from 550 kHz to 1650 kHz, and also given that the intermediate frequency is 450 kHz, and they have tuned the incoming signal frequency to 700 kHz. So therefore this 700 kHz is going to lie between the 550 kHz and the 1650 kHz, and we need to find what is the R, which is the ratio of the capacitor maximum by capacitor minimum we need to figure out, and also the image signal frequency, it is FSI or I. So in the question they are given I, but basically we are going to take it as a FSI. So FSI is called as the image signal frequency of the incoming signal. So that for incoming signal frequency is FS, or we can also call as a tuned signal frequency. So these are the two things we need to figure out in this question: the value of the R and also the image frequency we need to figure out. So in always in the super heterodyne, the base relation is Fs is called as the incoming signal frequency or the tuned signal frequency, and FLO is called as the local oscillator frequency, and SI is called as the image signal frequency, and the distance between these two frequencies is intermediate frequency, and also the distance between these two frequencies is called as the intermediate frequency. So we need to find what is this FSI, image signal frequency. So FSI is equal to Fs plus 2IF. So we know the value of the Fs, which is 700 kHz, and 2 into intermediate frequency is 450 kHz. And if you solve this numerical, we are going to get here 1600 kHz. So we can conclude that the value of the I is called as the image signal frequency which is 600 kHz. So now basically we know the relation between the frequencies is equal to F is equal to 1 by 2 by root over LC. So the remaining constants, remaining things I am going to take it as a constant. So now I am going to take relation between the frequency and the capacitor. So therefore the frequency is inversely proportional to under root over C, and similarly now I am going to take the C in this side. So therefore root C is inversely proportional to F0. So now I am going to take the square. So therefore C is inversely proportional to F0 square. So therefore now if you see carefully, if the capacitor to be maximum, the frequency has to be minimum, and similarly if the capacitor to be minimum, the frequency has to be maximum, because they are inversely proportional. So here we are going to take here local oscillator frequency. So here we are going to take the local oscillator frequency. So R is equal to nothing but C max by C minimum. See, the first one by second one, if you do the division, we are going to get here FLO max by FLO minimum whole square. So we need to find what is the FLO maximum and FLO minimum we need to figure out, and then we need to substitute those values, then we are going to get the value of the R. So therefore in local oscillator, if the FLO is greater than the Fs, means if the local oscillator frequency is greater than the incoming signal frequency, then always FLO is equal to Fs plus IF. Yes, FLO is equal to Fs plus IF. So therefore here Fs is a variable quantity, and always the intermediate frequency is always a fixed quantity. So if FLO has to be maximum, means the Fs also has to be maximum. So we know the Fs maximum. See here the Fs is going to vary between the 550 kHz to 1650 kHz. So therefore the maximum value of the Fs is 1650 kHz. So therefore 1650 kHz plus 450 is equal to 2100. So we got the FLO max is 2100 kHz, and now FLO minimum is equal to Fs minimum plus IF. So we know the value of Fs minimum, which is 550 kHz is the minimum value. So therefore 550 plus 450 is equal to 1000 kilohertz. So we know the value of the FLO max and FLO minimum. FLO max is 200 kilohertz and FLO minimum is 1000 kilohertz. So substitute these values here. So FLO max is 1200 kilohertz by FLO minimum is 1000 kilohertz. So if you do the square and if you do the division, we are going to get 4.41 is the correct solution of this question. So we can conclude that the value of the R is 4.41 and the intermediate frequency is 1600 kilohertz. And this is a basic relation between the incoming signal frequency, local oscillator frequency and the image signal frequency. So FSI is equal to Fs plus 2IF and FLO is equal to Fs plus IF. This is a basic relation. So with these relations we can easily figure out the value of the R and also the image signal frequency. So now we are going to solve the 82nd question. See the question here. When a radio receiver is tuned to 555 kilohertz, its local oscillator provides the mixer with an input at 1010 kilohertz. At the output, the another signal is also received along with the desired signal. So what is the frequency of the other station? So in the question they are given the incoming signal frequency is nothing but 555 kilohertz and the local oscillator frequency is 1010 kilohertz, and we need to find what is the image signal frequency we need to figure out. So what are the four options? Option D, which is 1465 kilohertz, is the correct solution of this question. So let's solve this numerical. So in the question they are given that basically FSI is called as the image signal frequency, or it is also called as the frequency of the other station. This is what we must figure out in the question. And also Fs is called as the incoming signal frequency or the tuned signal frequency. In the question they are given its value is 555 kilohertz, and similarly IF is called as the intermediate frequency, and FLO is called as the local oscillator frequency, or it is also called as the input frequency to mixer, which is given by the local oscillator, and its value in the question which is given is 1010 kilohertz. So out from this data we need to find what is the FSI we need to figure out. I have already told you the basic relation between the incoming signal frequency or the tuned signal frequency and the local oscillator frequency, or it is also called as the input frequency to the mixer, which is given by the local oscillator, and FSI is called as the image signal frequency, and the difference between these two signal frequencies is called as the intermediate frequency, and the difference between these two signals is called as the intermediate frequency. So basically we know the value of the Fs, we know the value of the FLO. So we need to find what is the value of the FSI we need to figure out. So basically what I am going to do is nothing but FLO is equal to Fs plus IF. So therefore FLO we know 1010 and Fs is equal to 555 kilohertz. So the only unknown quantity is the IF. So only one equation with only one unknown. So therefore IF is equal to 455 kilohertz. So 455 kilohertz is the intermediate frequency, but we need to find what is the FSI. FSI we need to figure out. So therefore now FSI is equal to Fs plus 2IF, or also we can also write it as which is FLO plus IF also we can write. So therefore here now I am going to take here Fs plus 2 into intermediate frequency. So Fs value we know which is 555 kilohertz and 2 into IF is 455 kilohertz, and if you solve this equation we are going to get 1465 kilohertz, and this is the image signal frequency, or it is also called as the frequency of the other station. So this is the correct solution of this question. So now we are going to solve the 83rd question. See the question here. So one of the main functions of the RF stage amplifier in super high return radio receiver is to. So what is the main function of the RF stage amplifier in the super high return radio receiver is to? So what are the four options? Option D, improve rejection of the image frequency. So it is going to improve the projection of the image frequency. So let's discuss something more facts about this one. This is the block diagram of the super radio receiver. Here this is the antenna. From this we are going to tune the incoming signal frequency, which is Fs. So this is called as a radio frequency amplifier. Then it is going to given to the mixer. So the input of the mixer is nothing but local oscillator. So therefore the local oscillator is going to give the frequency to the mixer. This input frequency is called as a local oscillator frequency, and the output is called as the intermediate frequency, and it is given to the intermediate frequency amplifier, and then it is given for the demodulation, and then it is given for the audio frequency amplifier, and then it is given to the power amplifier, and then we are going to listen to the speakers. So here these amplifiers, they need the DC signal for their operation. So therefore the DC signal is given for the RF amplifier, IF amplifier, and also for the demodulation. So therefore all these are going to require that DC signal for their operation. So if you see carefully, here IF is called as the intermediate signal frequency, and LO is called as a local oscillator, and here IF, this IF amplifier is going to reject the unwanted signals. this IF amplifier is going to reject the unwanted signals, and here if FLO is greater than the FS, then it is going to cover the entire frequency range with only the capacitor. So therefore if FLO is greater than the FS, then it is going to cover the entire frequency with only one capacitor. So if RF amplifier, this RF amplifier, this is the RF amplifier, it is going to reject or improve the rejection of the image frequency. So this RF amplifier is going to improve the rejection of the image frequency, and also it is called as the image channel rejection comes only from the RF amplifier. So therefore this RF amplifier is going to reject the or improve the rejection of the image frequency, image signal frequency, and image channel rejection is only comes, it is only this RF amplifier is the only thing out of all these blocks, only this amplifier is going to have the capacity to reject the image signal frequency. And basically we have also studied that one, FSI is called as the image signal frequency, or it is also called as the frequency of the other station, and FS is called as the incoming signal frequency or the tuned signal frequency, and IF is called as the intermediate frequency, and FLO is called as the input frequency to the mixer given by the local oscillator. Yes, FLO is called as the local oscillator frequency, or it is also called as the input frequency which is given to the mixer by the local oscillator. So basically we have also know the relation which is called as the, here the relation is nothing but this is called as the incoming signal frequency or the tuned signal frequency, and this is the local oscillator frequency, and this is called as the image signal frequency, and the difference between these two frequencies is called as the intermediate frequency, and it is also intermediate frequency, and it is a constant value always. So therefore here FLO is equal to FS plus IF, and similarly here FSI is equal to FS plus 2IF, or also we can write in another fashion which is FLO plus IF. So these are the three relations which you have to remember you have to solve any numerical in the super redundant receiver. So finally I am going to conclude that the only RF amplifier as the only amplifier out of all these blocks, it has the power to reject the image signal frequency, means it has the power to reject the or improve the rejection of the image signal frequency. Now we are going to solve the 84th question. See the question here. In a super heterodyne radio receiver, arrange the following components sequentially from the input to the output. The first thing is antenna, and the second thing is mixer, and the third thing is IF amplifier, and the fourth thing is audio amplifier. So in the question they are going to tell us that in super heterodyne radio receiver we need to arrange these block diagrams from the input to the output. So what are the four options? Option A, which is 1, 2, 3 and 4 is the correct solution of this question. So let's solve this numerical. So in this 84th question they are told that here this is the first one is the antenna, second one is the mixer, and the third is the intermediate frequency amplifier, and the fourth is audio amplifier. So we need to arrange sequentially in the as per the block diagram of the super heterodyne radio receiver, and this is the block diagram of the super heterodyne radio receiver. And if you see carefully, the first thing is the antenna, so therefore this is the first one, and similarly the mixer is also there, so second one, and similarly the third is the IF amplifier, it is also called as the intermediate frequency amplifier, and similar the fourth one is called as the audio amplifier. So audio amplifier, in the question they have not given the demodulation and the RF amplifier, but if you see carefully, this mixer, the antenna, mixer, IF amplifier and the AF amplifier, all these are in the sequential manner. So therefore the correct solution is 1, 2, 3, 4. So therefore this is the correct order in the sequential manner of arranging all these things as per the block diagram. So now we are going to solve the 85th question. See the question here. A signal x of t is equal to 3 into sine 2.2 to the power of 3t plus 2 into sine 2.2 660t. So at what sampling frequency should this signal be sampled to avoid aliasing? So therefore we need to find what is called as a Nyquist frequency. So the sampling frequency is also called as a Nyquist signal frequency we need to figure out. So therefore we can avoid the aliasing. So therefore out of the four options, option B, which is 2 into means 2000 Hz is the correct solution of this question. So let's solve this numerical. So this is a signal x of t is equal to 3 into sine 2.2 to the power of 3t plus 2 into sine 2.660t. So for this signal we need to find what is the sampling frequency, the minimum sampling frequency we need to figure out. So it is a summation of the two signals. So therefore sine 2 pi means omega t means 2 by ft. So f is nothing but frequency. So the first signal has a frequency fm1 is equal to 1000 hertz, and similarly this second signal has a frequency which is 660 hertz. So therefore it is a combination of these two signals. Of each signal frequency is 1000 hertz and the other signal has a 660 hertz. So we need to find what is the sampling frequency. Generally the sampling frequency has to be greater than or equal to 2 times the message signal frequency. So therefore the sampling frequency must be greater than or equal to 2 times the message signal frequency. This we have learned in the signal and system course. So therefore this is for the only one way if the message signal has only one message signal frequency. But if the message signal has so many message signal frequencies, means if the message signal has lot of frequencies, then we have to use this relation. It is nothing but the sampling frequency greater than or equal to 2 times of the maximum of the frequencies. Out of all these frequencies we need to take only the maximum value. So in this example there is only 2 frequencies, so therefore we need to take only 2 components. So therefore here, but we need to find what is the minimum signal sampling frequency. So therefore the minimum is nothing but we have to do the equate. So therefore 2 into max of fm1 comma fm2. So out of these 2 fm1 and ff2, the maximum value is 1000 hertz. So therefore 2 into 1000 is nothing but 2000 hertz, or it is also called as a 2 kilohertz. So therefore if you sample this message signal at this frequency, then by using the demodulation, then we can easily get the original signal back. So therefore there is no need of no aliasing effect will be there, means the higher frequencies will become the lower frequencies when we are going to do the aliasing, and this aliasing effect is going to absent if you do the sampling with this frequency. But if you do the sampling lesser than frequency, then aliasing is going to occur, then the higher frequencies will go into the lower frequency range. So therefore always you have to do the sampling above this minimum frequency only, but not the below of this the sampling frequency. So now we are going to solve the 86th question. See the question here. An analog signal has a significant spectral components from 1 kHz to 5 kHz. So what is the Nyquist sampling rate for this signal we need to figure out. So in this question they are given the message signal frequency is going to lie between the 1 kHz to 5 kHz. So we need to find what is the Nyquist sampling rate. Nyquist sampling rate is also called as the Nyquist frequency we need to figure out. So what are the 4 options? Option D, 10 kilo samples per second is the correct solution of this question. So let's solve this numerical. So in the question they are given the message signal frequency is going to lie between the 1 kHz to 5 kHz. This is the range for the message signal frequency. So we need to find what is the Nyquist sampling rate we need to figure out. So Nyquist sampling rate is nothing but the minimum sampling frequency we need to figure out. So basically in the sampling, by sampling we know that the sampling frequency must be greater than or equal to twice the maximum of all the message signal frequencies. So out of all the message signal frequencies, we will take only the maximum frequency. And if you see the message signal, the maximum frequency is 5 kHz. So therefore 5 kHz we need to consider. So 2 into 5 is nothing but 10 kHz. And the sampling frequency has to be greater than or equal to 10 kHz. Then only we can reconstruct the original signal back. So therefore here the minimum signal frequency is now only 10 kHz. This minimum sampling frequency is called as the Nyquist frequency, or it is also called as the Nyquist sampling rate. So which is nothing but 10 kilohertz. So therefore 10 into kilohertz is called as the samples per second. So therefore 10 kilo samples per second, then we have to sample this many 10 kilo samples per second, then only we can reconstruct the original signal back. So therefore we can conclude that the Nyquist frequency is also called as a Nyquist sampling rate. It is called as a minimum sampling frequency. So which is 10 kilohertz, means 10 kilo samples per second. This is the correct solution of this question. So now we are going to solve the 87th question. See the question here. The Nyquist sampling frequency in hertz of a given signal is given by. So this is the signal x of t. So for this signal we need to find what is the Nyquist sampling frequency or the minimum sampling frequency we get to figure out. So what are the 4 options? Option C, 1500 hertz is the correct solution of this question. So let's solve this numerical. So this is a signal they are given the question. For this we need to find what is the sampling frequency or minimum sampling frequency. It is also called as a Nyquist frequency. So basically before I solve this numerical, let me tell a small example here, small concept here. Sinc kT. This sinc kT is nothing but here sin pi kT by pi kT. This is the standard equation. So sinc kT is equal to sin pi kT by pi kT. So this is simply called as a sinc kT. So therefore now I want to find what is the frequency. This suppose let me take this as a signal. So I want to find what is the frequency of this signal. I have to figure out. So 1 by pi kt is nothing but it is a constant term. So it is a nothing but it's a variable. But here we need to find the sine omega t. So omega is equal to pi k. Sine omega t means omega is equal to pi k. So omega is nothing but 2 pi fm. So message signal frequency 2 pi f or 2 pi fm, pi into k. So therefore pi by k cancel. So therefore fm is equal to k by 2. So therefore this is the frequency of this signal. This is the frequency of the signal, but we know the standard equation, the minimum sample frequency is nothing but 2 into message signal frequency. So message signal frequency it is nothing but k by 2. So 2 into k by 2 is nothing but k. So we can conclude that the minimum sampling frequency or the Nyquist frequency is nothing but for this sync kt is nothing but k. So k is called as the minimum sampling frequency or the Nyquist frequency of this sync kt. And if you see here in this question also, all this in the formation of the sync but with some powers. So therefore we can conclude that suppose if f of t is equal to sync kt with the power of p, then the minimum sampling frequency will be, which is nothing but this p into k, you need to do the multiplication. And similarly, suppose if there is another signal f of t is equal to sync k1t whole to the power of p into sync kt k2t whole to the power of q, then the minimum sampling frequency is nothing but p into k1 plus q into k2. So this is the minimum sampling frequency. So if you compare these two equations, we can conclude that here, so p is equal to 3 and k1 is equal to 400 and q is equal to 3 and here k2 is equal to 100. So that is what I have written here. P is equal to 3, k1 is equal to 400, q is equal to 3, k2 is equal to 100. So if you substitute here p into k1 plus q into k2, and if you substitute those values 3 into 400 plus 3 into 100, so finally we are going to get here 1500 hertz. So finally what I am trying to conclude is nothing but for sync kt, the message signal frequency is k by 2 and the minimum sample frequency is k. So if you are going to take the power, any power, then the minimum sample frequency is just do the multiplication p into k. And similarly, if you multiply in this manner, it is nothing but p into k1 plus q into k2. This is called as the minimum sampling frequency or the Nyquist frequency. So now we are going to solve the 80th question. See the question here. The Nyquist sampling interval for the signal. So for this signal, we need to find what is the Nyquist sampling interval. Means the time period we need to figure out. So therefore, what are the four options? Option C, 1 by 700 seconds is the correct solution of this question. So let's solve this numerical. So for this signal, we need to find what is the Nyquist sampling interval we need to figure out. So I have already told you sync kt is nothing but sin pi kt by pi kt. So all this in the form of the sync kt and sync kt. So therefore x of t is equal to sync 700 pi t by 700 pi t and sync 500 pi t by 500 pi t. I have written in the standard form. So therefore now here this is sine, sync not, this is sine again. So therefore now sine omega t, so omega is equal to 700 pi, so omega 1, so this is the first signal, right? So omega 1 is equal to 700 pi and omega 1 is nothing but 2 pi fm1 is equal to 700 pi. So therefore if you solve, fm1 is equal to 350 hertz. So therefore this signal has a frequency of 350 hertz. And similarly this is sine omega 2t, so omega 2 is equal to 500 pi, so omega 2 is nothing but 2 pi fm2 is equal to 500 pi. So therefore if you solve, fm2 is equal to 250 hertz. So therefore this is the 250 hertz and these two signals are being added. So therefore we know the standard equation, the minimum sampling frequency is nothing but 2 times the maximum of the message signal frequencies. So out of these two message signal frequency, the maximum frequency is 350 hertz. So therefore 2 into 350 is nothing but 700 hertz. But we need to figure out what is the Nyquist sampling interval, means time interval we need to figure out. So we know the frequency, but we need to find what is the time period. So therefore frequency is nothing but 1 by time. So 1 by ts is equal to 700. So we need to find what is the sampling interval. So therefore ts is equal to 1 by 700 seconds. So therefore this is the correct solution of this question. In the question they have not asked the Nyquist sampling frequency, but they have asked the Nyquist sampling interval they have asked. So that's why we need to find what is the time period. So just ts is equal to 1 by 700 seconds is the correct solution of this question. So now we are going to solve the 18th question. See the question here. The minimum sampling frequency in samples per second required to reconstruct the following signal from its samples without distortion. So here we need to find what is the minimum sampling frequency. It is also called as the Nyquist frequency we need to figure out. And the signal x of t is also they are given. So out of the four options, option C, 6000 hertz is the correct solution of this question. So let's solve this numerical. This is the signal x of t. We need to find what is the minimum sampling frequency or the Nyquist frequency. So before I solve this numerical, let me tell a small concept here. Suppose there is a signal sine 2 pi fmt. So this signal has a frequency of fm. But if you are taking any power pa, then the new frequency of this signal is nothing but here the new frequency of this overall signal is nothing but P times the FM. So P times FM is the overall signal, and if you see carefully here sin omega t, so omega is nothing but 2 pi ft. So therefore the message signal frequency is 1000, but we are going to take the power 3. So therefore the overall message signal is going to have a frequency 3 times the 1000. So therefore 3 times the 1000 is equal to 3000 hertz. And similarly for the second signal sin 2 pi ft. So therefore the message signal frequency of this only this signal is nothing but 1000. But if you are going to take any square, then the overall signal frequency will be 2 times the power times the inside signal frequency. So 2 times the 1000. So therefore 2000 hertz. So therefore we can conclude that this total signal has a frequency of 3000 hertz and this total signal has a frequency of 2000 hertz. So now we are going to do the addition. So therefore we can conclude that the minimum sampling frequency is twice the maximum of the message signal frequencies which are present inside this signal, because we are going to do the summation. So therefore out of these two signal frequencies the maximum frequency is 3000. So therefore we can conclude that 2 into 3000 is nothing but 6000 hertz. So it is simply we can call it as a 6 kilohertz. So finally we can conclude that the minimum sampling frequency or the Nyquist sampling frequency is nothing but 6 kilohertz, and if you sample above this or at this frequencies, then only we can get the original signal back. Otherwise we are not going to get the original signal, but we are going to get the distorted signal. It is not equal to the original signal. So this is the last question of this lecture. See the question here. A signal x of t is equal to 6 cos 10 pi t is sampled at the rate of 14 hertz. To recover the original signal, the cutoff frequency of the ideal low pass filter should be. So here they are given the message signal also, and also they have given us the sampling frequency also they have given. So we will define what is the cutoff frequency of this low pass filter. In order to get back the original signal, we have to figure out FC. So out of the four options, option A, the FC has to lie between the 5 hertz and the 9 hertz. So let's solve this numerical. So before I solve this numerical, let me tell a small concept here. So this is x of t, this is a message signal. So we are going to take a pulse train. So P of t is equal to sigma k is equal to minus into plus into delta of t minus kts. So therefore this pulse train we are going to do the multiplication of these two signals, and the output of this signal is called as a s of t. So s of t is nothing but it is a product of the x of t and the p of t. So this x of t is now going to pass through the low pass filter. So after passing the low pass filter, then we are going to get back the original message signal x of t. X of t we need to get back here. So here we need to find what is this cutoff frequency. We need to find what is the cutoff frequency of this low pass filter. We have to figure out. So we know the value of the p of t. See, the Fourier transform of p of t is nothing but p of f, which is 1 by ts sigma k is equal to minus into plus into delta of f minus k fs. So therefore this is the p of f. So in the question they are given the x of t. X of t is equal to 6 cos 10 pi t. So from this we can get the message signal frequency, which is cos omega is nothing but 2 pi fm. So therefore 2 pi fm is equal to 10 pi, and if you solve, we are going to get here this signal as a message signal frequency of the 5 hertz. So therefore they are also given the sampling frequency. This p of t is going to have the sampling frequency fs is equal to 14 hertz. So we need to find what is the cutoff frequency of this low pass filter. We need to figure out. So therefore now what I am going to do is, now I am going to find what is this Fourier transform of this signal x of t. So basically for the a cos 2 pi fmt, the Fourier transform is a by 2 delta of f minus fm plus delta of f plus fm. So by using this formula here, a is nothing but 6 and 2 pi fm is 10 pi. So by using that, 6 by 2 delta of f minus fm plus delta of f plus fm. So fm is nothing but 5 hertz and 6 by 2 is nothing but now 3. So this is for 3. So therefore I have already told you this s of t is nothing but it is a product of the x of t and the p of t. So therefore s of t is equal to x of t into p of t. So if you are going to convert into the Fourier transform, it is nothing but the product is going to now change to the convolution. So therefore s of f is equal to x of f into convolution of the p of f. So therefore now if you do the convolution, we are going to do the convolution. So therefore here x of f convolution of the p of f. So therefore if you see carefully here, so therefore now what we are going to do is, this is the x. So therefore if you do the convolution, it is going to change in this manner. So therefore x of f is equal to 1 by ts sigma k is equal to minus into plus infinity x of f minus kfs. So it is nothing but here this x of f we need to shift from k is equal to minus into plus infinity through fs. So therefore now I am going to draw the x of f. X of f is nothing nothing but 3 delta of f minus fm plus delta of f plus fm. So therefore fm and minus fm. So the impulse area is 3. So this s of f is nothing but we have to shift this x of f by fs. So therefore at fs we need to shift here. So here also same thing here. It is also when k is equal to 0, same thing x of f is going to come here. So therefore this is the fm and this is minus fm. And then here when k is equal to 1, it is shifted by fs. So therefore again fs. So therefore here also this is nothing but same shifting. So we are going to shift this origin to the fs. So therefore this will become fs plus fm and this will become fs minus fm. And similarly now when k is equal to minus 1, now it is going to shift to minus fs. So therefore this is also here like this one. So therefore here this will become now, so minus of fs plus fm and this will become minus of fs minus fm. So this is the thing. Again if you take here k is equal to, so it goes on. So therefore this is the diagram of the s of f. But here by using the low pass filter we need to get back the x of t. So therefore, so now what I am going to do is, this is the original signal, right? So this I am going to take here, this low pass filter, this is the thing. So this is the original signal, right? So now I am going to use this low pass filter. This is the cutoff frequency. So if I take this low pass filter, all these components I am not going to get at the output. Only these two frequency components I am going to get at the output of the low pass filter. Then this is nothing but it is again the original signal x of t. So therefore here this frequency fc has to lie between the fm and fs minus fm. So we can conclude that this fc has to be lies between the, it has to lies between the fm and fs minus fm. So we know the value of fm, which is nothing but here fm is 5 and here fs is nothing but here 14. So 14 minus 5. So 14 minus 5 is nothing but again 9. So therefore here y less than fc less than 9. So therefore this cutoff frequency has to lie between the 5 hertz and the 9 hertz. Then only we are going to get back this original signal, because all these components are not going to come outside of this low pass filter. Only these two frequency components are going to get back out of the low pass filter. It is nothing but again original signal. So finally what I am trying to say is nothing but here s of t is nothing but the product, means s of f has to be the convolution of these two signals. And if you do the convolution of those signals, so we are going to get a pulse train of the x of f, means we are going to shift the signal through fs, plus 1 fs, 2fs, 3fs, 4fs and minus fs, minus 2fs, minus 3fs. We need to shift the diagram, and then we have to choose this low pass filter in such a manner, so therefore then we have to get only the two frequency components which are the original message frequency components. By using that relation, this fc has to lies between the fm and fs minus fm, then there will be no aliasing effect. So by this lecture we have successfully completed the 90 questions which are the previous year questions of the IES of Communication Systems of Electrical Engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever you upload a new video, the direct notifications comes on mobile. If any improvements needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.